So you can see it's finding prime numbers inside of other numbers, and it's going up by 2 each time. It's reasonably fast. But I want to make it a lot faster so I can do the much bigger numbers. Right now it takes double the amount of time. Right now it takes double the amount of time for every 2 additional bits in the number. If they're change the size from 30 bits to 40 bits, it doubles the amount of time of processing to 5 times that amount. So RSA isn't in trouble yet, but I think I can get there. So, how to factor large numbers very quickly. So I have this main routine factor, the number you're trying to factor, the first factor, the second factor, the bit column that you're processing, and has it reached its maximum? Maximum is basically an error code or success. So if it goes beyond the bounds, it terminates it too. So this is just how many times we've run this routine, and we're making sure that we have a terminating situation. And if it's less than 9, it's got to be a prime number, or it's got to be a prime number. If the number is less than, this almost probably never occurs unless it's a prime number. And so the square of bit, if it's bigger than twice the size of the number of bits, then it's done with. It's a prime number. Same here. Actually, this will occur several times. So when the 2 factors exceeds the size of the number, then you know it's not a viable path. And it's a binary tree. I'll show you that later. So then if 1 is greater than or equal to 3, we just check to see if it's a factor. If it is a factor, take out all the powers of that factor and put it in your list of prime numbers for the number, and then factor both of those. So we'll get a fully prime factorization of number. Same for 2. The second possible factor. Check to see if that is a factor. If it is, take it out and factor those. So here we're ORing bit with 1 and 2. You go up a value and then you check it for each bit the whole bit column. And if this is like what we did earlier, 1 and 2 here, 1 and 2 here, except this has gone up a bit. And then here we're testing all the possible cases. You go, is A, how many low end zeros do you have in A? How many low end zeros do you have in B? How many low end bits do you have for 2 with bit ords with it? Yeah, see, we ordered them here. And then double bit, just shift it up 1. Okay, and R is a temporary value, S is a temporary value. So here we clear R, and A with 1. Yeah, see, we're looping through this. We're ending A with 1. If it's 0, we're going to shift it right. So you're counting the zeros on the right edge of A until it's odd. And then you're putting that in A. So we had A up here where we did the test, and then we're counting the zeros in A and putting it in A. Same with B, C, and D. Now S is kind of tricky. If A is greater than B, give the string 2 A's, add 2 A's to it. If it's equal, add an A and a B. If it's less than, add 2 B's. So you can see where I'm going with this. I'm counting up the best possible fit for the number to progress with. And I just do that all the way down for A and B, A and C, A and D, B and C, B and D, and then C and D. So we have this string that looks something like this. It'll count all the, see how we're appending them and then checking them against the R value. Yeah, see, we're adding, this is how we construct the string A, and then the number of A's we have in S, B, the number of B's we have in S, C, the number of C's we have in S, D, and the number of D's we have in S. And here's the nitty gritty. I found out that when I did this process for odd numbers, odd possible factors, it would only come up with 6 possibilities out of the bunch that there could be. So if it's this pattern, then the bit column is either they're both 0 or they're both 1, because we have A, so they're both 1, and D, they're both 0 for that bit column. And here we have A4, B1, C1, D6. So in that case, it's the other way around. It's or it's the same deal as this one. They're either both 0 or they're both 1. Best possible solution. And then here we have A6, B1, C1, D4. And we flip this over because A is the favored possibility. So we got 1A, 2B. They're both 1 here instead of 0 because A was that possibility where they were both 1. And then here they're both 0. So you see I'm recursively going through this. There's a better way to do this. It requires a lot less resources. It's the binary tree. Just go through each branch of the binary tree until you find the factors. But I'm doing it this way currently because it's what I have so far. It's complete. And then A1, B5, C5, D1. So in this case, we have one bit that's true and one bit that's false. Here's the false one, here's the true one. Here's the false one, here's the true one. So going through all the permutations of the bits, you got 4 possibilities reflected by the 4 possibilities here. So here we're going through and testing it. Testing the possibilities depending. Yeah, you can tell there's going to be, it's possible to do other things than these 6, but they just don't occur. They could all be the same value, but that never comes up. And I'm not exactly sure why. And that's the end of factor. Isn't that fun? A new way for finding prime factorizations of numbers.